Hello and welcome to lecture 7. This is course on Aero engine gas turbine cycles. In last week we were discussing about the introduction to gas turbine engines which are being used for aircraft engines. Then we were discussing about important term, that's what is called thrust, and we tried to understand how all parameters which are related with the thrust formulation and what will be the effect of those parameters on overall thrust calculation. Then we were discussing about the engine performance parameters, where we have discussed about different types of efficiencies, which includes propulsive efficiency, thermal efficiency, propeller efficiency, overall efficiency. Then we started discussing about the takeoff thrust. We are also discussing about the specific fuel consumption, that is what is very important parameter. After looking at all these parameters, we also started discussing about the range factors, endurance factor, because that is directly related with the engine, but it is applicable to the aircraft in overall performance. Now today we are planning to discuss about the components which are being used for aero engines. So we will be discussing in detail about what all are the components which are being used for gas turbine cycles. Ideally, how we need to realize these components, and then after we will be discussing how they are different in terms of what we say actual condition. So let's start with the components here. So here if we look at, this is representing single spool turbojet engine. So this is the initial version of gas turbine engine, we can say, where we were having say compressors and turbines. So these devices are turbo machines, that is the reason why this is what has been named as say turbojet engine. Here if we look at very initial part, that is what is called diffuser. If we look at carefully, my entry area, if we look at, that is what is smaller. When it is moving towards the next component called compressor, where we are having larger area. Since it is having diverging passage, that is why it is defined or known as a diffuser. This is also known as say inlet or intake. People, they are using different terminologies. Now if we look at carefully, since my area, that is what is changing, that means we can say this is diffusing my flow, means it is decelerating my flow. So we can understand, if we consider our commercial flights, they are flying maximum in the range of Mach 0.8, 0.85. Same way if we are talking about say military engines, they are flying above Mach 1, maybe 1.4, 1.6 to 2.2. So with that speed, my component, that is what is starting with my engine, that means at the face of my compressor, we are looking for our flow to be slow, means it need to have your Mach number to be in the range of 0.4 to 0.6. That is the reason why we are having this diffusing passage. So today we will be discussing mainly on very first component, that is what is called diffuser. Now the question may arise, what all are the use of this component? So if we consider this as a diffuser, as we have discussed, we have the deceleration of the flow. Now that flow which will be entering inside my compressor. So its name says compressor, means it will compress my air. When we say compress, it means it is increasing the pressure. Now the high pressure, that is what will be giving the rise of temperature. So if we look at here, at the end of my compressor, I will be having air that has higher temperature and higher pressure. Now this high temperature and high pressure gas, that is what will be entering inside the combustion chamber. This combustion chamber where we are injecting our fuel. So basically in combustion chamber we will be having burning of fuel and air mixture. So once it will be burned in the combustion chamber, it will be generating the gas. That gas has very high temperature. Now this high temperature gas, that's what will be entering inside the turbine, where it will rotate the turbine wheel. When it will be rotating this turbine wheel, it will be generating the power. Now the question is, what is the use of this power? So if you look at carefully, this compressor and turbine, they are being connected on common shaft. So here if you look at, this is my turbine and this is my compressor, they are being connected on common shaft. So whatever power that will be generated by my turbine, that will be used to rotate my compressor. Now the question may arise, like, if this is the case, then I need to start my engine. So for that purpose, starters, they are being installed at the location here, which will rotate this engine at particular speed. Once it will be achieving that speed, it will start automatically for the suction of my air, and you will be having the rise of pressure, you will be having, say, injection of fuel and burning, and the turbine that will start rotating. Once it will be reaching to that speed, then automatically that starter will get disconnected. So do not get confused how the engine will be started with. Now this gas which is having high temperature, that will pass through this turbine, where it is subjected to expansion. Expansion in the sense my pressure will be reducing. Now that reduction in pressure, that's what will be passing through the nozzle. What gas we are having at the exit of my turbine, it is having very high energy. This high energy that will pass through the nozzle, and this nozzle, if we look at the entry area, we are having higher area, and at the exit we are having this area to be small area. So we can say this is my conversing passage. Now when we say conversing passage, that means this is a device which is being used for increasing the velocity, and that's what we are looking for. This is what is representing the exhaust from my nozzle. So in overall, if we try to look at what all are the use of these components, what it says, ingestion in the intake diffuser, it says inlet area diffuses the flow and decreases the velocity. That's what is required for the next component. Compressor, it will give the energy to the working fluid, and that's what will be increasing my total enthalpy. Now we will be discussing more in terms of thermodynamic term. Next component what we have is my combustion chamber, where the chemical energy is released in the burner, which will result in increase of even higher enthalpy. This higher enthalpy that will pass through the turbine, where it will be extracting the energy from the working fluid, and it will drive my compressor. Next component what we have is my thrust generation component, that we say is a nozzle. That's what will be converting my internal energy into the kinetic energy through the nozzle. So just try to realize, now we are discussing all our terminologies in terms of thermodynamics. It says what we mean by intake. So all air breathing engines installed in the aircraft must be provided with the air intake, or we can say ducting system, in order to diffuse the air from the free velocity or free stream velocity to the lower velocity, which is required by the next component, as we have discussed. Now the situation is, this component should provide the sufficient amount of air with maximum static pressure rise, with minimum total pressure loss, and it should give the uniform flow, and it should have minimum drag. We will see what all are these terminologies, because this is what is very important to understand in terms of analyzing our cycle. If we say for gas turbine engines, mainly turbojet engine, turbofan engine, turboprop engine, for that, for the compressors and the fan, they need to have the entry Mach number that is in the range of 0.4 to 0.6, or maybe sometimes it depends on a kind of compressor we are having. Now what all are the requirements for this intake? Suppose say you are given a task to select the intake, or say to design the intake, what all you will be looking for, because that is also equally important. What it says, it should have the lightweight and low cost of manufacturing. We must realize we are talking about the Aero engine, where our requirement is the maximum fuel economy. When we say fuel economy to be higher, that means my drag should be as low as possible. It says that's what is required, the lightweight kind of configuration. So intake should not be heavy. Next, it says it should give the adequate amount of mass flow rate at the variable Mach number condition, because our flight, our aircraft that will be flying under takeoff, climb, cruise or top speed condition. Suppose say if we are having this aircraft as a military aircraft, then we will be doing the maneuvers. So all these things, it should give the adequate amount of air mass flow rate. Next, what we say is it should provide a specially smooth flow into the compressor. That means low steady state distortion throughout the flight envelope. Same way, low dynamic distortion throughout the flight envelope, and it should be integrated nicely with the nacelle and fuselage so that it will be having low installation drag. Now let me put the point here. Airline company, they are buying the aircraft from the aircraft manufacturing company. Now these aircraft manufacturing companies, they are asking for the engine from engine manufacturing company. Now the chain is, we are having our engine and we are having our aircraft. Now the situation is this engine need to be fitted with your aircraft. So that's what is called inlet integration, or the integration of my intake with the aircraft, and that's what is a specialized field. People, they have spent their whole life for this integration kind of situations. So that is also one of the important domain, because that's what will be giving you, you need to utilize your aircraft in an efficient way, you need to utilize your engine in an efficient way. So all the information from the engine that will be given to say aircraft integration team or engine integration team, and that's what will be utilized by the aircraft manufacturing company. It is not ending there. Now the situation is, we have one of the restriction these days, that's what is with the noise generated. So it should not provide the high noise. So we need to have this intake that will give the quiet engine. Now suppose if we consider we are having the military application, or maybe if we look at our helicopter engines, for that maybe foreign particles that will be ingest inside the engine. So it should avoid that kind of situation. The next requirement what we say is a stealth technology, because since I will be having the variation of this velocity from very high velocity to the low velocity, that may give the signature, IR signature. So we are aware of what we know as stealth technology. So it should not provide the IR signature that can be detected inside the radar, and once it is detected, then you cannot save your aircraft from the enemies. So we need to be careful about that part. And very important is, you should have favorable abilities like accessibility, inspectability, reliability, maintainability and repairability, because it's not that it's one time installation. Maybe you need to remove the engine, maybe you need to go for the cleaning purpose, maybe you need to replace few components. So it should be taking care of everything. So that's what is coming in terms what we say as ergonomics. Now it should provide, that's what is very important, it should allow the engine to give the thrust growth, because that's what is very important for the aircraft. Now here if you look at this, all are representing the intakes what we are using for our aircraft engines. So very first, that's what is representing say GE9X. You can imagine the size, roughly it is around 3.5 meter to 4 meter diameter. It's not a small dimension, we can say. That's what is being used for our jumbo jet aircraft, okay, say like Boeing 777 having capacity of 312 passengers. Here if you look at, this is what is representing CFM56, that's what is used for your medium range aircraft, which is having capacity of 120, 180, maybe 220, and that's what is having the dimension of say maybe 2 meter. Here if you look at, this is representing the near mode. So, both this, if we look carefully, this engine, it is being integrated, it is being installed below the wing. Here in this case, these engines are buried inside the wing. So, it is of different kind of configuration. So, it's all depend on what all are the favorable conditions, what all the designers are thinking of, and accordingly they are making their design. There is no superficial rule. It's all your choice, it's all designer's choice to decide, and it should give what we are looking for. Here if we look at, this is what is with the jet engine where it has been installed above the wing. Here if we look at, this is what is representing Hunter, and if we look at carefully, this is the intake. Similarly, you will be having the kind of shape on the other side, and these together they are connected in Y shape, and that will give the common intake to the engine. This engine, it is been installed inside the fuselage. Now for military engine, this is what is a main requirement. You can imagine we are not having the fighter aircrafts with your high bypass ratio engines like what we are looking at here, because we need to install our engine within the fuselage. So my dimension, that's what is restricted. What is the reason? We can understand these wings we want to use for putting our weapons, and that's the reason why we are not having option to put the engine below the wing. Here if you look at, this is what is representing MiG-21, which is having intake in the front, and it is having this nose kind of shape. It is a sharp conical shape, and from here the air is going inside, and on the rear side we are having the engine. Here this is representing Su-30, where we are having two engines. You can imagine there are two intakes. These intakes are known as 2D intakes, and that's what is supplying the air to the engine. So it's all like what kind of application we are planning for. Now here we say this intakes, they are being classified as subsonic intake and supersonic intake. When we say subsonic intake, they are having application for transport aircraft, civil aircraft, and this transport and civil aircraft, what we are looking for, they are using say maybe turbojet engine, turbofan engine, turboprop engine, or the turboshaft engine. Same way when we are looking for the supersonic intake, which are flying above Mach 1, we can say they are special requirement for the military applications. So military aircrafts, commercial aircraft, say Concorde is one of the example, and missiles. So these gas turbines, as we have discussed in first week, they are having wide range of application. So one of the application, it is for the missile. Okay. Now here in this case, if we say we are looking for supersonic kind of flow, or we want to fly our aircraft at supersonic speed, my conventional intake will not help, and for that purpose we need to go with different kinds of intakes. It says axisymmetric or two-dimensional intake, and variable geometry or fixed geometry intake. When we say axisymmetric, you can understand here in this case we are having the central cone, or it may be having the kind of structure. This is what is representing the two-dimensional structure or two-dimensional intake, and this line, that's what is representing the shock, that's what is present at the entry. So just realize when we are having our flow, it is say supersonic flow. I need to decelerate that supersonic flow. That can be done by using the oblique shocks, and these oblique shocks finally will be terminated with normal shocks, and downside of our normal shock we will be having our flow to be subsonic flow. And here if you look at, suppose this is one oblique shock that will be terminated with my one normal shock, and downside if you look at, this is representing my subsonic intake. Same way in a variable geometry we are having different kind of mechanism. If you look at here, we can make this conical shape to move forward and backward. That's what will be to attach my shock, to place my shock as per the requirement. Here if you look at, this is what is representing for one of the fighter plane, where as per the requirement for different conditions, maybe cruise condition, takeoff condition, these ramps what we are having, that can move forward and backward. But the thing is, if we are moving with this kind of intakes, it will be more complex, but still as on today most of our fighter aircrafts which are flying at high Mach number, they are having this kind of mechanism. And when we say like fixed geometry, means in which we cannot vary this component, that those all components are fixed. Now, this is what is representing the evolution of fuselage mounted integrated intake. So, we can say during Second World War, these all intakes they are being developed. Now, we are moving towards say 2000, where we are having a different kind of intakes that people they are developing over the years with much more maturity. So, we must be aware of the generation or aircraft, say first generation, second generation. Presently, we are talking about the fifth generation aircraft, where we are having stealth technology, where this intake design, nozzle design, they are of main interest. Now, it says like if we are having Mach number in the range of 1.4 to 1.6, we need to go with the pitot kind of intake. It says like this is what is because we are looking for high total pressure recovery, we are looking for like small length and weight, that is what is a major concern. Suppose we are having say Mach number in the range of 2, it says external compression ramp system can be used for this purpose, and this is what is in combination as we have discussed earlier, maybe one oblique shock, two oblique shock, or maybe multi oblique shock that will be followed by normal shock, that kind of configuration people they are using for say Mach number in the range of 2. Suppose if we are talking about Mach number above 2, then we need to go with the mixed ramp kind of configuration. It says mixed compression multi ramp system. That is what is little complex, but yes, people they are using this for the special applications. Now, let us look at what is a scenario for the turboprop engine. Here if we look at, this is representing the turboprop engine, and here we are having the shaft, that is what is used for the connection of the propeller. So, you can see here we are having the intake, that is what is being placed. So, from here this figure if we look at, this is what is representing the intake for this engine. We need to understand here what is the use of this engine. So, we are not looking for the thrust generation where we are looking for large intake. We need to be little careful in terms of understanding. Here the whole requirement it is to generate the power, that is what is being used for rotating the propeller. In this case, if we look at these propellers, they are being placed below the wing here. In this case, here we are having the intake. This is what is representing the puller turboprop kind of configuration. Downside here if we look at, this is a pusher kind of configuration. The beauty of this engine is here we are having the intake, means intake is not being disturbed by the presence of my propeller. Here also if we look at carefully, I am having my propeller shaft, that is what is off center, and that is what is taking care of putting this propeller in the center of my wing. So, next application if we are talking of, that is what is with the turbo shaft engine, which we are using for the helicopter engine. Here if we look at, we are having two engines, they are being placed on the top, and we must realize the reason why we are putting those engines on the top. Our requirement is to supply the power to this shaft in order to rotate these rotors. So, that is the reason why it is been installed above this. Okay. Similarly, here if you look at, this is representing say transport helicopter. Here if we look at carefully, this is representing the LCH, where the engine it is been placed like this. Okay. Same way here if we look at, we are having the side by installation for Bell engine. This is what is with the fighter helicopter, where we are having two engines, they are being placed on both the sides. So, the situation is the intake what we are discussing at this moment, it looks simple, but when we are going with the application, especially for the aircraft, maybe commercial aircraft or maybe for say fighter aircraft, it is most challenging design. Same way if we are looking for say turboprop engine or turbo shaft engine application, where this intake design it will be very challenging. Now, let us try to analyze this part in a different way, because this is what is our requirement and we need to insist more on this kind of analysis. What it says, my inlet area diffuses the flow and decreasing the velocity for the next component. That is what is my requirement. So, let us assume this as my diffuser or the inlet. We can say it is having diverging shape, and in order to analyze, I will be selecting this as a control volume. When I say control volume, my mass flow rate, that is what is entering here, and my mass flow rate, that is what it will be leaving here. In this case, if we look at, we are having say heat transfer as well as my work done. So, let us make certain assumption. It says my entry mass flow rate and outlet mass flow rate, they both are same. Assuming there is no bleed and a leakage, assume there is no loss mechanism, we can say that is what is representing my reversible condition. My Q is 0, we can say this process there is no heat transfer, that is the reason we are considering that as a adiabatic process. My W, that is what is 0, means there is no mechanism for the work to be done on this control volume. So, under that condition I can say my flow through the diffuser is reversible and adiabatic. Okay, means this flow is isentropic flow. So, here if we write down our energy equation, it says my Q, that is what is delta E minus W. This Q we are considering there is no heat transfer because there is no temperature gradient, there is no work done. Means my delta E, if we consider, or my E, that is what is remains constant. In this condition, I cannot consider this as a actual working condition, because what is happening, we are having the irreversibility, that is what is coming into the picture, and these irreversibilities are because of my wall friction, my shock structure, as we have discussed earlier. Now, if I consider this is my control volume, and for that if I will be using my steady flow energy equation, this is what is the formulation for my steady flow energy equation. I here put the point, maybe you just repeat or just revisit your thermodynamics book, that is what will be helping you in understanding these equations, because this week that is what is more focusing on this steady flow energy equation and its application. Here my Q, that is what is 0, I say my W, that is what is 0, and if I will be putting this elevation also to be 0, then I say my delta H, it is nothing but delta H static plus this velocity. If I am rewriting that, it says my H plus V square by 2 equal to Hs plus V1 square by 2. Now, this is what is representing very important property, that is what we say my total enthalpy. What it says, my total enthalpy, that is what is remains constant. So, inlet is a process where we can assume it to be reversible and adiabatic, in which my total property they are not changing. The thing is my kinetic energy that will be converted into the static energy, but its summation remains constant. We need to understand this part, this is what is very important. Now, let us try to understand in this scenario. Suppose if I consider this is representing my TS diagram. For that TS diagram, I can say this is representing my free stream condition. Suppose if I consider there is no flow kind of configuration, my M infinity is 0, I can say this same property I can take as a total property. But suppose if I consider I am having my kinetic energy, that is what is supplied to the engine, means my engine is in flying condition, my Mach number, that is what will be coming into the picture, it is more than 0. So, this is what is representing my velocity component. If that is the case, I will be having the property, that is what is defined as a total property. So, let us try to understand what exactly is the meaning of that. Suppose if I consider this is representing my ambient condition, this is my entry condition and my exit condition. So, let us put this is what is representing my entry condition P infinity. I say I am having my flow, that is what is going inside my intake, that is what I say it is giving me my total property, it is V infinity square by 2 Cp, that is what is giving me my P0 infinity. Now, this is what is representing the property as we have discussed in first week as my total property. Now, if we consider, I say this is isentropic flow. Okay. Now, if I consider this as adiabatic process as we have discussed. So, I can say my H01, H02 and H0 infinity, that is what is remains constant. And if I will be putting my total pressure at the outlet of my intake, that will come as P02. Now, when I say this P02, I am having, there is a loss of pressure, that is what we have discussed, and this is what is representing my irreversibility associated with the process. Now, if I will be joining this, this is what is representing my actual process. Now, suppose if I consider my static pressure, if I want to calculate, it says this is representing my static pressure, it is 0.2. Now, this is what it says. Because of this irreversibility, we are having the rise in the entropy. Now, let me put this point as a infinity point, this I am putting as a isentropic process 02S, and here I am putting this as a 02. Okay. Now, this is what is representing my ideal condition 0, it is from infinity to 02S, and from infinity to 02, that is what is representing my actual condition. So, we must realize this is what is representing my inlet process on HS diagram or TS diagram. Now, suppose if I consider, say this is what is my intake, and for that intake if we are considering, this is representing my free stream condition. Okay. Now, suppose if I say I am on the ground run condition, for that ground run condition I will be having my free stream flow, that is what will be entering from some infinite distance, which is having area say A infinity. This is what is getting accelerated here at the entry, and downside, since it is having the diffusing passage where my deceleration of the flow is happening. Suppose if I consider my climb condition, my speed, that is what is increasing, I want my flow to be enter with high velocity say V1. If this is what is our configuration, we can say my free stream area, it is decreasing. Now, if I consider say next condition, say high speed condition, high speed cruise, that is what is having Mach in the range of 0.85. So, if we look at carefully, this free stream area again is reducing. So, if we look this area outside, it says it is making a diffusing passage, and we are having other diffuser, that is what is a physical diffuser. So, it says I am having the external diffusion, that is what is happening outside my intake, and I will be having internal diffusion, that is what is happening inside my diffuser. Now, if we go to the next, it says I am having the condition, that is what is my top speed condition, where my Mach number is in the range of maybe 0.95. So, what will happen? Since I am increasing my speed, that means my area from where air is entering inside my passage, that will be reducing. Here also we are having say diffusing passage, but we must realize the aerodynamics of the diffuser. Since my diffusing angle, that is what will be large, that is what will lead to give the flow separation, and that is what is creating trouble downstream of my engine. I should avoid this kind of situation. So, all aircraft, say commercial aircraft, we look at, they have been designed for maximum speed that cannot be flown beyond that speed. Okay. Now, let us try to look at this condition what we were discussing about the takeoff and cruise condition. Suppose if I consider this is representing my station 1 and station 2, station 2 is my compressor inlet. I am having second condition, that say cruise condition. For this cruise condition, I am having station 1 and station 2. What is happening here? What we know? If we look at here, since my flow is getting accelerated, that means I will be having the drop of pressure. Suppose my pressure at the entry or at the upstream condition is P infinity. At the entry of my intake, I will be having drop of static pressure, and this is what is acting as a diffusing passage. That is the reason I will be having the rise of pressure within this diffuser. My next interest is what is happening with my velocity. It says since I am having this passage area as a converging passage area, that is why I will be having the rise of velocity, and this is representing my drop off velocity. Now let us look at what is happening with my total pressure. So here if we look at, this is representing my total pressure condition. When I say my total pressure condition, this is representing almost my total pressure, that is what is remains constant, and here I will be having slight drop of pressure. We know what is the reason, because of presence of my boundary layer, because of growth of my boundary layer, and that is the reason why we are having the screen friction losses that will come into the picture. We can represent that on TS diagram. I say this is representing my P infinity, that is what is my entry static pressure. If I will be adding V infinity square by 2 Cp, that is giving me P 0 infinity, just realize this part. Here somewhere I am having say drop of pressure, that is why I am putting this downside, it says my P1 pressure. Since within my diffuser I am having say total enthalpy or my total temperature, that is what is remains constant, but there is a drop of pressure, that is the reason why I will be having P02, that is what is less than that of my P0 infinity. And if I will be putting my C2 square or V2 square by 2 Cp, that is what will be giving me my static pressure. So if we join these together, that is what is representing my static pressure rise. Okay. Now this is what we see, we are having our V1 to be greater than that of my V infinity, we are having our P1 that is less than my P infinity, my P01 and P0 infinity, that is what we are assuming to be same, there is no change, and it says my adiabatic condition. Now here if we look at say next condition what we have, it is my V1 that is what is less than that of my V infinity, because we are talking about the cruise condition, where we will be having our pressure to be greater than that of my P infinity pressure. My total pressure upstream and at the entry of my intake, that is what will remains constant, and I am having my total temperature, that is what is constant. So let us look at, it says from P1 P infinity to P1 I am having the rise of pressure, that is what is represented by P infinity to P1. Again in a diffuser we will be having the rise of pressure, it is P1 to P2. If we are talking about the velocity, my entry velocity is higher, my velocity at V1 or station 1 that will be lower, and further it will get decelerated. Here in this case same way my total pressure, that is what is remains constant. Okay. Now if you want to put this as a scenario, it says this is representing my P infinity, I am having V infinity square by 2 Cp, this is representing P0 infinity, P02, same way I can calculate what is my P2, but here in this case my P1 that is what is higher than that of my P infinity. So this is what is representing the rise of my pressure from P1 to P2. Now what it says, under this condition, for takeoff condition my static pressure rise, that is what will be greater than that of my cruise condition. Okay. Now in order to check the performance of my intake, we are introducing the parameters. Very first parameter we are putting is say isentropic efficiency. So here in this case, similar to what we have discussed in previous slide, we can say from infinity to 0 to S, that is what is representing my isentropic process, and from infinity to 0 to, that is what is representing my say actual process. So efficiency of the diffuser, it is given by H02S minus H infinity divided by H02 by H infinity. It means my isentropic work done divided by my actual work done. So that we can represent in terms of my temperature ratio. Here this temperature ratio, this is representing the isentropic process. So we can write down, it is given by 1 plus gamma minus 1 by 2 into m infinity square. So those who are not having the background of gas dynamics, it is preferred that you just read the book, any book of gas dynamics, where you will be studying very first part, that is what is called isentropic flow. So that fundamental, that is what will be useful here. Since this course is not been designed for starting from that fundamental, so straight away I am putting this equation here. Now, if I will be writing that, we can write down that in terms of my pressure ratio. So, it says my P02 by P infinity to the power gamma minus 1 over gamma minus 1, and this temperature, that is what we are representing in terms of gamma minus 1 by 2 into m infinity square. So, in overall if we look at, it says my pressure ratio, that is what is given by 1 plus diffuser efficiency gamma minus 1 by 2 m infinity square to the power gamma over gamma minus 1. So, there is no need to mug up this equation. From the fundamental you can easily get this part. Now, this is representing how my pressure is changing. If you recall, I was discussing, we are looking for my static pressure to be higher, we are looking for my total pressure loss to be minimum. That means our major concern is with the pressure. What is happening with the temperature? So, if I write down the temperature equation, it says my T02 by T infinity, that is what is given by 1 plus gamma minus 1 by 2 m infinity square. To your surprise, here if you look at, for the pressure we are having diffuser efficiency term, and here for temperature we are not having diffuser efficiency term. The reason here is my outlet temperature of the diffuser is independent from the losses, because we are assuming our flow process to be adiabatic process, and that is the reason why this diffuser efficiency is not coming. When we will be starting with the cycle analysis, that time this point is very important. So, just try to recall, try to remember this thing. Okay. People, they are using different terminologies for defining the performance of the intake. One more parameter they have defined is stagnation pressure ratio. So, this stagnation pressure ratio, it says it is outlet pressure from the diffuser to the free stream pressure. Now, here I am writing P02 by P infinity. If you try to recall, we have derived our efficiency equation, diffuser efficiency equation in terms of P02 by P infinity. So, that is what we are writing as a P02 by P0 infinity into P0 infinity by P infinity. Now, here this is what is representing my isentropic process. That is the reason it is written as 1 plus gamma minus 1 by 2 m infinity square to the power gamma over gamma minus 1. This is my total pressure ratio that I am writing as a R suffix D. Okay. Now, let us try to combine all these equations. If we will be putting, it says my diffuser efficiency, that is what is a function of my pressure ratio. This pressure ratio, that is what is known as a total pressure recovery, or it is called recovery factor. So, this recovery factor, if you look at, that is what is given by P02 by P0 infinity, and here it is a function of my diffuser efficiency. So, different users, different fabricators, different designers, they are using different approaches to define the efficiency or the performance of my intake. Now, here if we look at the terminology of diffuser efficiency and total pressure recovery, you will see everything we are discussing in terms of free stream condition. So, we should not forget what is happening with my intake actually. So, that is the reason why people, they have defined the third terminology for the intake. It is defined as an internal efficiency. Now, this internal efficiency, if you look at, so this is what is representing my internal condition station 1 to 2, and that is the reason why we are writing this internal efficiency term as H02S minus H1 divided by H02 minus H1, because we are more interested what is happening for internal part. So, here also we know our process for isentropic process we can represent in terms of say Mach number, and if we will be writing this equation, it says my P02S by P1, that is what is my entry static pressure, that is function of my internal efficiency. So, when we are solving our numerical, when we are reading the leaflet that's what is given by engine manufacturing company or by intake company, you need to be very careful which parameter they have defined. Is it diffuser efficiency, pressure recovery factor, or say internal efficiency? So, in order to build the confidence in terms of understanding, let's take one numerical. So, it says a gas turbine engine intake has total to static pressure ratio. So, you can say it is P02 by P infinity, it is 1.025 and 1.453. The aircraft is flying at say two different Mach numbers, Mach number 0.2 and at 0.8. What it says, we need to calculate the diffuser efficiency and stagnation pressure ratio for both the cases. So, here we are taking our gamma equal to 1.4. Now, let us try to understand how do we solve this numerical or what do we do with. So, what is my requirement? I need to calculate what is my diffuser efficiency and stagnation pressure ratio. So, let us put the hint here, and I am sure with this you can solve this numerical, and in next lecture we will be discussing about how to solve this numerical and how to do the calculation. So, it says we are having given data in terms of diffuser efficiency. Okay, we are say looking for say our Mach number. In this case, we want to calculate what will be our total pressure ratio. Okay. So, this total pressure ratio, that is what is a function of my diffuser efficiency and it is a function of my Mach number. Okay. So, I am sure what all we have discussed in this lecture, that is what will be giving you very good understanding of your intake. These intakes may be of any component or any engine, maybe turbojet engine, turbofan engine or turboprop engine. For all these engines, my intake performance, that is what will remain same. So, we are starting everything from the fundamental and slowly we will be moving towards the actual requirement. So, here we are stopping with. Thank you very much for your kind attention. In next lecture, we will be solving this numerical and we will move forward with the next component. Thank you.